All right, thank you so much for the organizers, and thank you for everybody that's been here. It's been a really just wonderful time. I've gotten a lot of new ideas. It's been great catching up with friends and getting to know new people and seeing just some amazing research, and also seeing that a lot of us are still trying to understand some things. So I'm going to tell you a little bit about some work in my lab at BYU. I have to point out, because BYU makes me, anytime I say the word terahertz in a public talk, I have to point out a financial interest in a company that I formed. So anyways, there you go. Like I said, I'm coming from Provo, Utah in the mountains, and but it always feels good to feel like I'm coming home. I did my postdoc at the Paul Scher Institute, and so coming back to Europe is just wonderful. In my lab, we do a lot of research involving terahertz. About half of what we do is looking at new materials to help generate terahertz light. And then we use the terahertz light to do some interesting things that I'll tell you about today. So this is a question that's on a lot of our minds. Can we create a magnetic moment or magnetic order in a non-magnetic material? We've seen this wonderful work from Nicola Spalding's group and others that have stayed in the field. Here's a few kind of theoretical works that have been done on this, and I think there are more that my list is not complete now. And then we've seen a few of these experimental works where we're trying to excite chiral phonons and see if there is a magnetic response in the material. And so here's two works that have been mentioned a number of times this week. And so this is Martina's work here. Now, in both of these works, they measured a Faraday signal or a magnetic Kerr signal that is equivalent to approximately 1 Tesla external magnetic field. And so the question is kind of like, and this is what some of Hiroki's measurements were trying to get at, is this some kind of effective field in the material? Is it a true magnetic field where magnetic field lines would extend out of the material? One of the interesting things to think about is what this even means when these materials are all, or many of them, like strontium titanate, is diamagnetic material. Materials I'll tell you about today are diamagnetic as well. So we tried to do some similar kinds of measurements in my lab on a few different materials. And I'll tell you about some differences and similarities between some of those previous measurements. So we're looking at lithium niobate. This work that I'm going to tell you about is just as of, I guess, sometime during the night. It's now on the archive. And so you can look at that. And if you'd like to give me any feedback on what's there, I'd appreciate it. But we're going to look at lithium niobate. And we're going to excite with our terahertz pulses the lowest frequency E-symmetry mode. And so this is what the motion of the atoms in that mode looks like if you're looking at it from one view or a different view of the unit cell. If our terahertz pulse is polarized along this blue arrow, which is representing the mode effective charge, we'll excite this motion. But it's a doubly degenerate mode. And so if our terahertz is polarized in this direction, and it's going into the screen in this picture, we'll excite this motion. And you can see, there we go, that say you just track this yellow lithium atom, and this one versus this one, you can see that the motion is perpendicular. And the first time I thought about trying to excite motion that's not just going in a straight line was listening to Nicola Spalding talk at a GRC meeting in Galveston, Texas a number of years ago. And she had the whole crowd like waving our arms around and doing circles and things. Anyways, I think she just had to step out. But anyway, so I appreciate her kind of introducing me to this world and a number of others. So what we're going to do is we're going to take a pair of terahertz pulses, one vertically polarized, one horizontally polarized, with just the right phase delay between them, so we can then excite this kind of loop motion. And if you're going to take pictures, you should take a video of this one. One of my students, Lauren, coded this in MATLAB. And so that's where these pictures come from, which is kind of fun. Now, lithium niobate is a little different than some of the other samples because this particular mode, as well as the lowest frequency A1 symmetry mode, they form Phonon-Polaritons in the material. And so this is a picture of the Phonon-Polariton for this E mode, the dispersion curve. And so we can see how the frequency of this Phonon-Polariton changes as we change the wave vector. This is the spectrum of the terahertz pulse that we're using in these measurements. And so when the terahertz pulse enters the material, it excites this Phonon-Polariton all across this dispersion curve where we have frequencies in our terahertz pulse. So we're not exciting just a single frequency that's oscillating, but we're exciting all of these frequencies along this Phonon-Polariton dispersion curve simultaneously with our terahertz pulse. And so I can tell you that. I'll also just mention that we've done some recent work where we've measured this. And this is some collaborative work with Elsa Abro and Steve Johnson and Laura Benfato. And these are the postdoc and PhD students that are writing up the paper right now. But with the identical terahertz pulse, if we change our probe wavelength, we can pick out different points on the dispersion curve to show that we are exciting all along this dispersion curve with a single terahertz pulse. So now, instead of just this kind of ion loop motion that's happening in the crystal, we have this truly chiral motion as the Phonon-Polariton propagates into the depth of the material as the terahertz enters. All right, so that's what we're exciting in lithium niobate. So how do we excite this kind of chiral motion? We want a pair of terahertz pulses, one that's vertically polarized, one that's horizontally polarized. This is what our experimental setup looks like. And so we take the output of an OPA. The signal pulse from the OPA excites terahertz in one DAS crystal. The idler output excites another DAS crystal. We create these pair of terahertz pulses. They're brought parallel next to each other, and then they overlap and cross, and the fields add at the sample position. And we can control the timing between the two. And so if we have the two terahertz pulses that are nearly identical lined up right next to each other in time, we'll get linear polarization at 45 degrees. And if we just have the right delay between them, we can make this terahertz pulse, that the combined pulse has this kind of circular component to the polarization. All right? So we're going to take this circularly polarized terahertz pulse, and then we're going to excite this motion. If we just had a single mode, this is a model of what that motion might look like for like a vertical and a horizontal vibrational mode that we add together to create this kind of circular motion. And so the motion gets excited, the phonon mode damps out over time, and so we can kind of see this ion loop motion going over time. And you'd expect if we were to induce a magnetic moment in the material, it would kind of follow the envelope of these oscillations, all right? And so in this setup, we're going to probe the response of our sample with 800 nanometer light, doing an ultrafast Faraday rotation probe. And so we're going to look at changes in the polarization of linear probe pulse. And then we're going to think about what this might mean in terms of how much the probe is being rotated in comparison to a magnetic field that might be generated, right? Now, I think the thing to remember in this consideration is that where this kind of equation was developed was from Faraday rotation measurements, where you're applying an external magnetic field to your material, and you're looking at some probe polarization change, which will give you the Verdet constant for that material. So we're kind of taking this. We measure a polarization rotation. We have a Verdet constant for lithium niobate. We know the thickness of our sample, and then we're going to kind of see what is this magnetic field that we would have to apply in this other situation, even though our situation is a little different. So just kind of keep that in mind. All right, so this is what our signal looks like that we measure. And they're quite large changes in polarization angle. So we got about 0.1 degree change in polarization angle as a function of time. It kind of turns on and slowly turns off. And if we have our terahertz polarized in one direction, we could imagine exciting these ion loops in a particular direction. So this is an actual measurement of the terahertz electric field using electro-optic sampling, where we can see this kind of going this clockwise direction in this picture. And so that would create a magnetic moment going in one direction. we can change from right to left circularly polarized terahertz, and that would flip the direction of this magnetic field if that's there in the sample. And we can see when we change the direction of the polarization of our terahertz, our signal indeed flips. All right, so we're doing what we think we should do. Now, because of our experimental setup, we can control the relative delay between our two terahertz pulses over a whole range, and we can measure kind of an average ellipticity angle for our terahertz pulse, and then see what the signal looks like. And so these three signals here are for the kind of maxima and this minimum. And so this is like at negative 45-degree ellipticity angle and positive 45-ish degrees. And then we get another one just because of how our terahertz pulses line up here. And so we can see these signals. And that's what the actual terahertz pulses look like at each of these positions. So we can see it's kind of clockwise and counterclockwise and clockwise again in this direction. All right, so we get this maximum signal when the terahertz is most circularly polarized. Because it's a broadband terahertz pulse and our two terahertz pulses aren't identical, it's not a perfect kind of circular polarization. You can't really get a perfect circular polarization with a single cycle pulse anyways. All right, now one thing that's a little different from some of these previous publications is how we actually construct this signal. All right, so if you remember, we have 2 terahertz pulses, and we have here this kind of differential chopping scheme where in a sequence of 4 laser shots, we can measure both terahertz pulses together to create this chiral terahertz pulse, and then just one, which is vertically polarized, one that's horizontally polarized, and then we just measure the probe with no pump pulse. And so if we look at the signals from each of these, it's kind of interesting to think about a little bit. So this is the polarization rotation angle signal, this Faraday signal that we measure when we just have a vertically polarized terahertz pulse. And so in this case, if it's just a linearly polarized terahertz pulse, we should not be exciting anything chiral in our material. Yet we still see a polarization rotation. And in a certain extent, that makes a lot of sense because these are Phonon-Polaritons that we're probing, and their Raman tensors have off-diagonal elements which will rotate the polarization of probe light. All right? But this is emphasizing the fact that there are other signals besides magnetic signals that can rotate the polarization of our light in these measurements. All right? So that's the vertically polarized terahertz pulse. That's the horizontally polarized terahertz pulse. This is the combined circular terahertz pulse that has both the horizontal and vertical together at the appropriate delay. And so this signal right here is actually what is equivalent to what's being reported in those 2 papers. But we're able, in our setup with this differential chopping scheme, to subtract off these contributions from the linearly polarized terahertz and then get this, this signal that I have been showing you so far. Okay? Now, we can also do this at a variety of different delays, not just some of them that I showed you before. And so this is kind of what, if we're changing the delay between our 2 terahertz pulses, measuring as a function of time, that's our combined signal. And then this is the signal from just the vertically polarized terahertz pulse and the horizontal polarized terahertz pulse. And then this is when we've subtracted that out. And so these kind of stripes that we see here, if we took a stripe along here, that would be one of these signals that we show. Okay? All right, so now we have this kind of signal that has these linear field contributions removed. We're plotting it as a function of polarization rotation angle. And we can then look at our Faraday effect equation with the Verdet constant for lithium niobate and change our change in polarization angle into a magnetic field as it would be if it was an external magnetic field applied to the sample. And so for this, this is one of our signals. This gives us a magnetic field estimate here in excess of 10 Tesla. All right? So that's if the signal arose from pure external magnetic field. Okay. Now, as I've said, we're all trying to understand this a little more. And is that really the field that's present in the material? Is that what's an external? Is it an effective magnetic field? So I'll come back to that idea at the end. But we're just going to go with this right now. So we wanted to better understand, is this arising from circular motion of phonons, like we've discussed? Could it also be an inverse Faraday effect, where we have the electric field of the light just kind of distorting the electron cloud and making circular currents there? And so we can go ahead and model each of these responses and compare it to our signal. So first we'll look at the electronic response. We measure our Terets field directly, and so we can just plug that into a model where the inverse Faraday effect magnetic field would be related to E cross E dot, where E is the terahertz of our circularly polarized Terets pulse. And this is what we would get. And we can see that this pure electronic model doesn't match our data. All right? So then we can go and model this circular phonon motion. Again, we're doing this for basically all the points on the Phonon-Polaritons dispersion curve and kind of adding up a total sum of that signal where the magnetic moment is related to Q cross Q dot. Q is the phonon mode motion variable. And here we see that the pure phonon model also does not match what we measure. And so we look at a combined model where the only free parameter here was looking at the relative amplitudes of the inverse Faraday effect versus this phonon model. And that combined black line, you can see, matches our data really well, which was kind of exciting to see. And so you can see this initial field here, or this initial signal here from the inverse Faraday effect, and then this kind of a little bit slower signal from the vibrational model. They can add up, and we can kind of see contributions from each to our total signal. Now, whether or not this is inducing this strong of a magnetic field in the material, I am not 100% sure. But whatever is leading to this signal, this model of this chiral phonon-polariton motion plus this circular electron motion from the terahertz pulse seems to match our signal really well. And so that was interesting to look at. OK, so that's our results for lithium niobate. And I also wanted to show some recent results from a different material that we've looked at in beta barium borate. So this one's a little different. It doesn't really form the phonon-polariton in the same way that lithium niobate does. It also has lots of modes in the frequency range that we can generate. So we can typically generate terahertz pulses from about 0 to 6 terahertz in our setup, and there are lots of vibrational modes that are IR active in that frequency range. This is actually why BBO, a lot of people use BBO as like a nonlinear optical crystal for second harmonic generation. This is why it's terrible at terahertz generation, because all of these modes absorb any terahertz you might generate. All right? The phase matching is terrible as well. All right, so we're going to take an Z-cut crystal where the different directions, we're only sensitive, we only absorb, or our terahertz light only interacts with these E-symmetry modes. And this is a transmission measurement. It's not a very pretty one, but you can see that there are these 3 E-symmetry modes that absorb here. There's another big one here that's kind of getting into the noise, but it has a really strong absorption here. And so instead of exciting just a pair of degenerate modes that would make this add up to make this circular motion, we now have several modes. So we have these 3 sets of E-symmetry modes. They each have perpendicular degenerate modes. Those correspond to these frequencies here. This last one that I highlighted right here, this is a picture of what the eigenvectors look like. And so here's one, here's the other. If you combine them with the right phase, you can kind of make this circular motion of the ions. And then there's this other one here that has a really strong absorption. So the terahertz in our measurements now are going to excite 4 pairs of E modes to induce circular atomic motion. And the 4 modes are at these frequencies here. And so We're not necessarily going to have perfect circular motion from each of these modes because the phase between our 2 terahertz pulses might be optimized for one of those frequencies, but not all of them. But they will all be excited by our terahertz pulse. And so this gives us a little more fun playground of things to look at and think about. So we can do this differential chopping to look at our different measurements. This is the signal from the vertical terahertz, from the horizontal terahertz, from the combined terahertz, and then we subtract out the linear components and we get this. In BBO, we see a little more of an oscillatory motion from these modes that are both IR and Raman active. Here is the signal that we see from these kind of 3 main points as we change the terahertz ellipticity angle. So kind of these 2 positive points and this 1 negative point down here. And we're thinking about, so as we're changing from these to this, we're changing from like circular right to circular left our terahertz, just like we did with lithium niobate. And so we can kind of see motion, right? We're exciting motion in one direction and the other. One of the things that is really fascinating with BBO, so lithium niobate, we saw this very large polarization rotation signal of about 0.1 degrees. You can see this one in BBO for a thinner sample is even larger, right? So we're getting a 1 degree polarization rotation. The Verdet constant for BBO is kind of similar to lithium niobate. And so this would be equivalent to, I just put greater than 10 Tesla here, but this would be more like 50 Tesla, which is a really strong magnetic field. And again, I think all of us are thinking a little more about what it even means to have a really strong magnetic field external and what that does to a diamagnetic material internally, or what it would mean to have a magnetic field inside of a diamagnetic material. And so anyways. One of the things that we are trying to do with BBO is do some modeling with some help of some first principle calculations that we've done in my group, where we can calculate the frequencies of these modes and the mode effective charges and the eigenvectors. And then we can use our real experimental terahertz pulses to then look at the motion of the atoms. These are going kind of circular counterclockwise. These are going more clockwise, right, as we're changing the terahertz polarization from right to left, circularly polarized. And then we can start to look at this potential phonon magnetic signal and how much of that arises from each of these pairs of modes. And so this is the signal that we model using all of the modes. But then we can kind of look at what the signal would look like if we only excited the pair of modes at 2.1 terahertz, or that's the one that contributes the most. And then this 4.4 terahertz that has really strong oscillator strength, even though it's kind of outside of our terahertz bandwidth a little bit. Anyways, but we can kind of see contributions from each of these pairs of modes to our signal and think about what's going on. And this total signal matches well this kind of ellipticity angle dependence that we see here. Here are some questions that still remain. Is a magnetic moment really as strong as these Faraday rotation measurements suggest? So we've heard here, and you've seen some posters here, of a few different ways people are trying to get at that. I liked Hiroki's idea of looking at the field on the back side of the sample. It's very similar to some work that's being done with Mikael Furst and Andrea Cavalieri. I saw a poster from Chiral, yes, about an external material where you're trying to measure the magnetic field outside. Cliff Allington had a poster that I'm particularly fond of because I'm involved in that work as well, where we tried to use X-ray measurements to and Hiroki's involved in that as well, to measure the magnetic moment in the material. All right, so we did some measurements on europium titanate at the LCLS at SLAC. And here's some pictures of the actual experiment. We built a custom double pulse terahertz setup, just like we have in my lab, so we can make these chiral terahertz pulses. Martina was involved in those as well. Yeah, great. A lot of people. Go look at the author list on Cliff's poster. There's a lot of people there. So here's some pictures from Beam Time. Oh, there's Martina. Here's some of my students, Matt and Alex and Enoch, that were there. And anyways, we're trying to do these measurements and see what's going on. This is just a brief summary. If you had a chance to talk to Cliff, he gave a better overview of this. But this is the idea of the measurement. We send in a circularly polarized terahertz pulse to this ETO thin film. And we're looking at diffraction to 2 different peaks to be able to track the motion of the atoms. But what's unique here is we're doing this with circularly polarized X-rays. And we're also simultaneously doing XMCD measurements to try to see if there's a magnetic field that we can detect on the europium atoms. Now, one of the key things that we took away from this is that we indeed are exciting circular motion of the ions in europium titanate, where if we look at these 2 diffraction peaks, the signal is the dark blue line or the lighter blue line, but you can see that they're out of phase, which indicates that they're moving in a circle. If we change our terahertz from one direction to the other, we make them circular going the other way. So we are inducing this kind of circular motion. Here is a little picture. This is an early one. I think Cliff had a better one on his poster of what that motion of the atoms might look like this was room temperature data. Interestingly, the XMCD data did not show a really strong magnetic field. We at least were able to get kind of an upper bound, but maybe there's some other reasons this isn't working out 100%. So let me summarize. Intense terahertz light can drive fundamental excitations like phonons far from equilibrium. Chiral terahertz launches chiral phonon-Polaritons in lithium niobate. I'm really interested in seeing how this, doing some more measurements where we kind of look more at the propagation of the phonon-Polariton. In our setup, we could remove signal contributions from linear fields. We also saw extremely large polarization rotation in BBO. There's some questions that remain on the strength of the magnetic field, and we and others are exploring other probes to look at and try to better understand what's going on with this. So thanks to you all. It's been a lovely conference. So thank you for organizers for organizing this. Thank you all for your attention. Special thanks to the Gordon and Betty Moore Foundation that's funding some of this work in my lab. And then especially Enoch, Megan, Matt, Alex, and Ravi that have been some students and postdocs working on this. And then some collaborators from Switzerland on some of the FEL work. So thank you all.
Thank you, Jeremy. Thank you.